Welcome to section 2.1. So in this particular section, we're going to be looking at what happens if we change the initial conditions slightly. So looking at this differential equation here, we're given a starting position of x0 is 2. But let's focus on the right-hand side. The right-hand side is factorable. I can factor an x out, which means that this right-hand side could be 0. Well, when is it 0? It's 0 when x is 0 or x is 1. Let's see, what does that mean? So if our initial condition x of 0 is 0, that would mean that the derivative is 0, and if the derivative is 0, then we started off at 0 and our solution will remain 0 for all time. If my initial condition is 1, well again, if it's 1, the derivative is 0 and our solution is going to remain at 1 for all time t bigger than 0. Well, what if my initial condition is some number in between 0 and 1? Well, in that case, then the right-hand side would be bigger than 0, which says that the derivative is positive, and if the derivative is positive, then my solution will be increasing. Well, increasing to what? Well, it's increasing to 1 because once it gets to 1, the derivative is 0. What happens if my initial condition started off bigger than 1? Well, in that case, the right-hand side is going to be negative. The derivative is negative, which says that my function is decreasing. Well, decreasing how far? It can't go decreasing forever. It decreases until it gets to 1, where the derivative is 0. Now remember, our initial condition we were given was that x of 0 is 2. So we're starting off bigger than 1, so our solution should be decreasing. All right, so I'm going to separate our problem and do something easy on the right. This will give me minus t plus c. The left, we need to use a technique called partial fractions, seen in Calculus 2. So I'm going to rewrite this particular rational function as a sum of two pieces from the bottom. Multiply both sides by 6x, x minus 1, and so we get this relationship. And then in the technique of partial fractions, I let x be different things to solve for a and for b. So if x is 1, the a part is gone, and I can get b as 1/6. If I let x be 0, the b part is gone, and I can solve and get that a is minus 1. So this difficult integral is now the sum of these two easier pieces. And so if I integrate 1 over x, I get ln absolute value of x. Integrate this, ln absolute value x minus 1, and this stuff was from the right-hand side. So now, multiply through by 6, and then I'm going to move this term to the front. So I've got a difference of 2 logs. Well, if you remember back to our properties of logarithms, the difference of 2 logs is the log of a division. All right, so we're there. Now I'm going to need to use e to get rid of the logarithm like we've done before. And so I get the inside part, e to this stuff. Remember, this is times e to the c, but we're still calling this thing c. All right, so my initial condition was at time 0, we were at 2. All right, so fill in 2, 2, and 0. I get that c is 1/2. All right, so c is 1/2, and so I've got this. And now I need to solve for x. But that's kind of messy to keep carrying this with it. So I'm just going to call this thing a for convenience. Could have called it whatever you like. So multiply both sides by x. Got that. I'm going to move this x to the right. Factor out the x. And so I get that x, my solution, is -1 over a minus 1. So again, I did all that so I wouldn't have to keep carrying that term. All right, so it's there in the denominator. I got a common denominator here. I can pull these two together, and now this will flip. And so I get 2 over 2 minus e to the minus 6. So you can see that the long-term behavior here is going to make this go to 0. And then I would have 2 over 2, which is 1. So it's decaying down until we get to 1. All right, well, let's see. What else can we see here? If I look here at these different graphs, it is the graph for c. Here's 1, here's 0. Remember, if we started between 0 and 1, it was increasing. If it were in between bigger than 1, we were decreasing. And here in the little dotted blue is our solution starting off at time 0 of being 2. And you can see this here. If t is 0, this is e to the 0, which is 1. 2 minus 1 is 1. And 2 over 2, 2 over 1 is 2. All right, so similarly, looking here at question 2, I'm focused on the right-hand side. The right-hand side is 0 here. All right. On this part, it's 0 when x is 8. So if I pick something in between 0 and 8, that means this term is going to be less than 0. So the derivative is going to be negative. And so our solution should be decreasing towards 0. What happens if we started off at our initial condition bigger than 8? Well, bigger than 8 means that this item on the right would be positive and the solution will continue to grow. If we started off at 0 or 8, the derivative would be 0 and our function would remain constant for all time. All right, so we separated the problem. Right-hand side is easy. I'm going to integrate 1 dt. On the left, I need to use partial fractions again. So multiply through by that denominator. Pick x is 0 and 8 so we can solve for a and for b. All right, let's put all that in, pull out some of the constants. And so I'm integrating each of these pieces. All right, ln absolute value of x minus this ln. But again, the difference of two logarithms by properties of logs is the ln of the division. Right-hand side was t plus c. And so we've got this left-hand stuff equal to the right. All right, but I can't take E yet because I have this constant stuck in the front. So multiply through by a negative 24. All right, so now I have this ln. And I can take E of it. All right, so E of the ln gives me the inside part. E of this part is here. And E of all this junk we just call C again. All right, so what do I have? I know at times 0, we were at 1. All right, so 1, 1, 0. So C is a minus 1/7. So again, rather than carry this thing around, I'm going to call it A. Multiply both sides by x minus 8, and then start trying to get x by itself. All right, and so finally I do get there, and so I'm going to plug in what I know about A. So, but this is a 1 over A, and a 1 over this would mean that this is a positive number. And I'm going to get a 7 in the front. All right, got a minus 8 still stuck there. So I've got a positive 8 over 7. And so if I let t go to infinity, this term will grow on the bottom. It'll keep growing, meaning our item is going to decay down to one of our zeros, which was 0. So looking at the graph here, remember, if it's 0 or 8, it stays there. If it's a number between 0 and 8, it decays towards 0. Here's our initial condition in the blue dotted line. And if I start off bigger than 8, remember the solution kept growing. All right, in question 3, we have something about population. All right, so we have dp dt is AP minus BP squared. And then there's some things about BAP is time rate of births. Deaths are given by BP squared. A and B are just proportionality constants. We start off with an initial population, an initial births per month, and an initial deaths per month. And they say, let's show that the limiting population is given by the initial birth rate, initial population, and initial death rate. Well, if I look at the right-hand side and I factor out of this a BP, I get something that looks like this product. And, well, what are the zeros? The zeros there are P is 0, and if P equals A over B. So these are the two zeros, and A over B is going to be the limiting population. So if I start off at either place, those are constant. If I start off between 0 and A over B, it's going to increase to that limit. And if I start off bigger, it's going to decrease. All right. And so the trick here is just to look at A over B and realize, well, what do we have? If I take A, P0 times P0 divided by B, P0 squared, notice that is just A over B, but AP0 is B0, and BP0 squared is what the initial death rate was. So just some manipulation with symbols. All right, in question 4, we have an alligator population. We have a birth rate of AP squared this time. So not the death rate, but the birth rate. And the death rate is BP. So again, I'm going to get a threshold population. All right. And so the question is this: if the initial population is 100 alligators and there are 10 births per month, 7 deaths per month at times 0, how long does it take us to reach a threshold that is 20 times the threshold? All right, well, let's see. What is the limiting population? So again, this is how you get what the limiting population is. And so plug in the numbers that we have for death, birth, initial population of 100 alligators. And so the threshold is 70. So we need 20 times that. Or the question is, when will we reach 1,400 alligators? So here's where we're starting off. Here's the threshold. So we are certainly bigger than the threshold, so we're going to grow. So how long does it take to get there? All right, it turns out that our solution for this problem looks like the following. And if we plug in the values that we have, so for M, for initial population, so we get something that looks like the following. And it turns out that K, my rate here, is 0.001. Okay, so again, that's looking at this situation. All right, so we have, starting off at 100, it's growing. Birth rate, death rate, threshold was 70. All right, so let's figure out when we are 20 times the threshold. And so if you grind through this, you find that T is the ln of 19 over 6 divided by 0.07. So that was my rate, remember, my K. And so 16.46 months, or you could round it to 16.47 months. All right, we have some salt. Looking at the salt, it looks like our population model this time, which we just did in not the previous problem, but the one before that. And so looking at that, we have a differential equation that looks like this. Factor this out. So I get that the limit is M, and the M is 600. All right, so we have all this information about what we started off with, K and all that. So let's see, anything we need from here? If at times 0, we had 40 grams at times 0, how long will it take to get an initial 40 grams? And if we let this thing keep going, well, how much will the most we ever get is? Well, that's the limit, and that limit was 600. All right, so getting our basic equation going, we'd like to know if we start off at 40, we want 40 more, so we want to know when we will reach 80. So it's just a question of grinding through this exponential equation until we get what t is, and so about 0.26 seconds.